And so today we have Christian Lau from the University College of London for a seminar. Christian received his master degree in mathematics and physics from the University of Glasgow 2021 on applying Bayesian modeling techniques with normal grid profiles. And now he is a PhD candidate focusing on understanding dynamics of substorms, utilizing a combination of ground-based observatories and spacecraft data. And in addition to this, he's also interested in forecasting magnetospheric dynamics, understanding the connection between solar wind and Earth's magnetosphere. Today, he will talk about issues identifying substars. So please, Christian.
Cool. Thank you so much for the introduction, Jose, and thank you for the invitation to speak today too. Yeah, good afternoon in America. Yeah, I'm Christian Lau, I'm third year PhD student, as Jose said. Today I'm going to speak about some of the work I've been doing during my PhD, addressing some issues around substorm identification. So before we talk about identifying substorms, it's first we've got to introduce them. So what is a substorm? Simply, it's a global instability of the solar wind magnetosphere ionosphere system. The classical description of the substorm includes three phases: growth, expansion, and recovery. The growth phase is thought to be initiated by a southward turning of the interplanetary magnetic field and consequently enhanced dayside reconnection. This acts to add to the stored magnetic flux in the tail lobes, resulting in a thinning of the plasma sheet and a slow enhancement of the cross-tail current. The onset of the substorm expansion phase was initially identified as localized brightening of an equatorward arc followed by its spread poleward and azimuthally by Akisofu 1964. This coincides with the formation of the substorm current wedge in the inner magnetotail, where the intensified current is disrupted and a pair of field-aligned currents couples the magnetotail to the ionosphere. Further out, magnetic reconnection creates an isolated plasmoid that is accelerated out and ejected from the magnetotail. During the recovery phase, the magnetosphere returns to its quiet time configuration, but there are still complex auroral displays that happen. So hopefully I've introduced to you what a substorm is and its kind of subsequent phenomena. Now, why do we study substorms and why do we care about the substorm intervals? Well, firstly, it plays a key role in changing the configuration of the magnetosphere, like I've described earlier. It transports stored magnetic flux and plasma from the tail region to the inner magnetosphere on the day side. It can cause enhancements of the radiation belts. It can energize the ring current. It has the possibility of increasing the intensity of the precipitating flux. It can change the ionospheric conductivity. And finally, for I think most of you that at UNH can cause extreme rates of change of the surface horizontal magnetic field. So we're interested in substorms since it controls the flow of energy in the magnetosphere. And during substorm intervals, significant events occur that are localized within specific magnetospheric regions that many of our community care about, whether on the ground, in the ionosphere, or further out in the magnetosphere. So now we know why we care about substorms. How do we identify them? Well, firstly, we can identify them by leveraging the original definition of a localized brightening of an equatorward arc of the aurora that is followed by expansion poleward and longitudinally. The video on the right here will show some prior auroral activity that's likely to be a pseudo breakup before there's a substorm onset that occurs at 1429 UT. You'll hopefully be able to see a clear local brightening at that time, followed by its expansion. And then afterwards, there's a more complex auroral display during the rest of the expansion phase and into the subsequent recovery. We can also identify substorms from their ground magnetic signatures caused by the formation of the substorm current wedge. One at high latitudes where the disrupted crosstail current flows through the ionosphere, and one at mid latitudes where the magnetic signature is thought to be caused by field-aligned currents. The figure on the right here shows a schematic of the substorm current wedge, and in subfigure B, the expected deflections of the ground magnetic field at 30 degrees in latitude due to the field-aligned current legs. Additionally, we can identify substorms from particle injections, which are defined as a sudden increase of particle fluxes at geosynchronous orbit. The example on the right here is from the Borowski et al. 1993 paper, where they visually identified onsets from the CPA instrument on the LANO satellites. However, there's a problem in substorm identification, since the signatures may not always be detectable for every substorm. Spacecraft might need to be in the right position, and our magnetometer arrays are not equally distributed. And also, these signatures are not unique to the substorm phenomena. Finally, there's a degree of subjectivity in identification, whether that be the author's discretion when identifying auroral displays by eye, or the threshold set when using an automated scheme. To illustrate this, I have an example. So this is just an example interval where we see some event correspondence and also disagreement between substorm signatures. In the middle here, we have the auroral zone indices, SML and SMU, with the Newland-Gerlov onset times indicated as vertical red lines. At the bottom, we have the mid-latitude positive Bay index with the Chu et al. 2015 onsets indicated as purple lines. At the top, we have auroral images during some selected times, 3 of those times being when Frey et al. 2004 identified an onset, and the one at 4:37 UT being a time that an onset was observed by Newland-Gerlov, but not by Frey. The colored arrows below the images and the Y and N in those images indicate if that auroral image is associated with a substorm onset. We can see here that the first auroral onset is missed by the MPB index method of Chu, but the MPB index method is able to resolve the remaining 2 onsets. As for the SML method, we see that it has resolved all the Frey onsets, but also triggers off another magnetospheric phenomena at a more complex interval of the aurora. So there is a brightening, but it's at the poleward edge of the aurora instead. Another example is shown here, where Frey et al. Identified 2 auroral onsets with a clear brightening of the aurora, but neither of these events were picked up in the automated lists of Newland-Gerlov Chu, though there are enhancements of these indices around these times. So for example, at 7:28 UT, where we have the localized brightening at local midnight, there is an SML Bay, and there is an increase in MPB index that is impulsive, but these are not being large enough to trigger the automated algorithms. And similarly, for the 22:46 UT onset, there is an SML Bay and MPB impulse, but again, not large enough to trigger the detection algorithms. So clearly we have a couple of problems in substorm identification. Furthermore, the advent of automated schemes have presented another issue. Before talking about it though, it's important to discuss the first substantial catalog of substorm events by Borowski et al. 1993. Where they found substorms at a rate about 1,500 per year, which corresponds to about a mean waiting time or mean time between successive substorm onsets of about 5.7 hours. On the right here, we have the waiting time distribution or a waiting time plot, which is just the time between successive substorm onsets, where we see a sharp peak at 3 hours and then an exponential decrease with a long tail. This behavior in the waiting times of successive onsets has been backed up by other studies, such that the standard waiting time between successive substorm events has been somewhat codified at around 3 hours in the literature. And this distribution here is further evidenced by the Frey et al. Auroral events. However, recent automated identification schemes based on the magnetic indices have found many, many more onsets, such that the peak waiting time is now sub 1 hour. And actually it's caused a divergence in the modality of these distributions. So the previous distribution you saw was just unimodal with a sharp peak at 3 hours. The automated identification schemes now have both unimodal and bimodal, kind of indicating 2 modes of reaction for the substorm phenomena. So there's quite a big problem there. And furthermore, there's the superposed epoch profiles of SML around these onsets can show really large differences between the events being identified, with some events being extremely large, almost double the SML Bay of others identified. So there's a clear discourse on what constitutes as a substorm, and there's a divergence of events that are being studied. This means that it's increasingly difficult to verify any models or theories, as one can tailor and optimize to one event catalog, but may not be capturing dynamics of the whole system. In that case, one of the primary goals of my PhD and my work here at UCL has been to evaluate the relationship between different substorm signatures and help the community progress to a common set, or at least a common description of substorm events. So to do this, we just ask 4 simple questions of substorm signatures or identification methods. So say you're leveraging 2 substorm signatures, A and B. How often do you see signature A with signature B? How often do you see signature A without signature B? How often do we see signature B without signature A? And how often do we see neither signature A nor signature B? And these are just answers to the elements of a contingency table, a confusion matrix for those of you who do model evaluation. So the elements, in terms of model evaluation, you're normally going off a ground truth. So in our case, we don't have a ground truth, since the assumption is that there's no ground truth substorm event. So in our case, we there's signature A and signature B, but in confusion matrices, it's usually a ground truth and a forecast. And these are just answers to our 4 simple questions before. So true positives are how often we see signature A with signature B. False negatives are how often we see signature A without signature B. False positives, how often we see signature B without signature A. And a true negative is how often we see neither signature A nor signature B. The next problem to solve is then how to populate this contingency table, since we have a set of time series rather than categorical data. We do this by splitting the time series into a series of windows. In our case, we split them into 30-minute windows. We do this because it's a conservative estimate for the lifetime of a substorm expansion phase, such that we can say if 2 signatures are occurring for the same substorm rather than for subsequent events. Once we have split the time series, we ask the 4 questions for each window. We have signature A in the top left here. I'll just go through this figure. Signature A in the top, so it should be in the bottom. We have substorm onsets that populate these the time series, and as time goes from left to right. So our first window on the top left here is has an event in both signature A and signature B. So it's a true positive, and we labeled it as so in green. The next window along has no event in signature A and no event in signature B. So it's seen as a true negative, labeled in white. Then the following window has an event in signature A, but not in signature B. Therefore, that's a false negative, labeled in yellow. And then the next window has no event in signature A, but an event in signature B, such as a false positive and labeled in red. So once we've labeled all the windows, we just count the number of each type and fill in the elements of a contingency table, as so. So this table corresponds to the time series above, where there's one true positive, 2 false negatives, 2 false positives, and 1 true negative. However, the contingency tables themselves are not very understandable. Therefore, we have to transform them in some way to get some insight. We do this in the form of metrics. Those of you in forecasting or model evaluation are probably very familiar with this, as metrics are a key tool in evaluating how good any forecast or model is. A really simple metric that we could use is the percent correct. And this is just our true positive and our true negative divided by the number of windows that we have. Toy example is, to illustrate this, I'll use a toy example. So let's say we have signature A that occurs 15 times, signature B that occurs 15 times also, across 100 windows. And then they occur common 10 windows between them, which means that they miss each other 5 times each. This gives us a percent correct of 0.9, which is, I would argue, is pretty good. However, there's a flaw in this metric, since you can get quite a good score, a percent correct of 0.7. And as you can see in this toy example here, signature A and signature B have not occurred for the same window at all. So you can in the forecasting and model evaluation framework, this is kind of similar to the concept of hedging, where if you have a rare event that you want to forecast, in this case, creating a model that forecasts a non-occurrence can achieve quite a good metric score, but ultimately the forecast is completely uninformative. And as substorms are rare events, occurring approximately 3 hours, which is an order of magnitude larger than our event window size of 30 minutes. We need a solution that can account for low rates of occurrence and putting greater value to true positives when the signatures occur in the same window. One way of doing this is by applying a probabilistic treatise to the contingency table with the assumption that two signatures are stationary and independent. So stationary meaning that the probability of occurrence is fixed across time, and independent meaning that there's no dependence of a signature A on signature B for occurring and vice versa. So back to our simple question framework, you can just ask, what's the probability of getting a yes in signature A? And in that case, that's just a true positive plus a false negative over the number of windows you have. In this toy example, that's just 0.15. And then you can ask another simple question. What's the probability of seeing a yes in B? That's just true positive plus false positive over the number of windows you have. In the case of our toy example, 0.15. And then you can get your probability of getting a true positive given these two probabilities of occurrence. So that's your probability of seeing a yes in signature A, the probability of saying a yes in signature B. And that's 0.0025 for this example. You can play the same game for the no's, but in this case, for signature A, you're taking the false positive and true negative for signature A, and then for signature B, you're taking the false negative and true negative, and you evaluate for our toy example, probability of no for each as 0.85. And then you can get your probability of a true negative as your probability of a no in either signature A and signature B. And that evaluates your probability of true negative of 0.7225. Then you can evaluate this thing called a random percent correct, and that's just your probability of getting a true positive plus a probability of true negative. And then for the toy example case, that's 0.745. Then we make use of this in the way of the Heidecke skill score, where you evaluate the percent correct that you evaluated for this contingency table, minus the random percent correct, over 1 minus the random percent correct. The one here might seem a bit arbitrary, but it's the ideal percent correct score achievable when all the elements are either in the true positive or true negative case. And in plain English, the Heidecke skill score quantifies the improvement over any chance agreement. I should say it goes from -1 to 1. Scoring -1 is when you get all the elements in the false positive or false negative classes, or when you're perfectly obtaining the wrong class. So you actually just need to flip your forecast to get a perfect score. Scoring 0 is equivalent to a random level of agreement and 1 a perfect agreement. So the toy example from before, we get a percent correct of 0.9, a random percent correct of 0.745, and this evaluates a Heidecke skill score of 0.61. The Heidecke skill score can also be written in this form using the elements of the contingency table directly. So, and if you would like a full probabilistic derivation, please read Havarinen in 2014. And back to our toy examples. So I said before that you got quite good scores, even when you hedged. Now, as before, we got percent correct 0.9 of 0.7. The Heidecke skill score evaluates a 0.61 for this toy example, where the two signatures do see each other. But the second toy example now evaluates a Heidecke skill score of -0.08 when they don't see each other. So it's actually worse than random chance agreement. This is exactly the characteristics of any metric that I would like for my research, and it allows us to ask a very simple question. How similar are substorm onset lists? So to do that, we analyzed 10 substorm onset lists or catalogs, one of them identified by I, that's the Frey Auroral onset list, and 9 automated methods, 4 of these leveraging electrojet enhancements, 2 detecting ground perturbations due to the field-aligned currents of the substorm current wedge, and finally, an automated method on geosynchronous satellites to detect particle injections. And the results can be seen here. Again, I want to reiterate the Heidecker score indicates improvement over random chance agreement of events. And this subset only includes the best methods or highest scoring methods from each data set. The best association I've seen is between the Newell and Gerlov 2011 onset list and the Chu et al. Onset list, achieving a Heidecker score of 0.33. Coincidentally, they're also the 2 best scoring onset lists. And the particle injections show the poorest associations with the other lists. You can see here that it actually scores 0 when compared with the Frey or all image list, so that any agreement between these 2 event lists is kind of due to chance. I can empathize that the Heidecker skill score is not the most intuitive metric to understand, so I also make use of another metric to illustrate this. That is the true positive rate. Simply, that's how many events of signature A was also seen in signature B. So in the elements of the contingency table, that's just your true positives over your true positives plus false negatives. In the first toy example, 10 events, you have 15 events, windows labeled as yes in signature A, and 10 of those windows are have a coincident event with signature B. So you get a true positive rate of 0.66. And in the second toy example, you don't see any coincidence between these 2 events. So you evaluate a true positive rate of 0. And the results using this metric, I actually need to explain a little bit more. There's now directionality in our skill score. So it's important to remember what list is labeled as what in this case. So in our previous language, the reference here means it's signature A, and the comparison signature B, such that the true positive rate indicates the percentage of events in the reference list that's also seen in the comparison list. So you can see from the heat map on the right here that even the best associating lists have less than 50% event coincidence. That's actually quite shockingly poor. And the highest association, the highest true positive rate is when you use the Chu list as the reference or signature A, and the Newell and Gerlov 2011 list as the comparison or signature B. And it means that 45% of Chu events have a coincident Newell and Gerlov events, and that corresponds to about 1,500 events that are common to both Chu and Newell and Gerlov. As you can see here, only 5% of Frey onsets have a coinciding particle injection with it. So it shows you that it is a really low amount of coincidence between these 2 signatures. And that 5% kind of corresponds to about only 100 events common to both the particle injections and the auroral onsets. So to answer my simple question from earlier, how similar are substorm onset lists in the literature? With less than 50% event coincidence, not similar at all. This leads us to ask 2 more questions. What's causing the disagreement between these 2 different lists? And can we filter out these errors? I just want to go on a brief aside on another substorm onset list called SOPHY. So substorm onsets and phases from indices of the electrojet. It's a method, it's a non-parametric method that identifies substorm phases from percentiles of the yearly rate of change of SML. Additionally, it also attempts to distinguish substorm events from other magnetospheric phenomena. It does this by leveraging the SMU index, flagging intervals where there's a comparative increase in SMU as a decrease in SML as enhanced convection intervals. So on the right here is just an example time series where I've labeled each phase of the substorm during that time series. So SOPHY has evaluated the first period in green as growth, then the SML bay here as expansion phase, the subsequent increase in SML as a recovery phase. Then there's another period of growth that happens. There's another SML bay. However, this SML bay corresponds to, it's correlated with the increase in SMU at that time. Therefore, the SOFI algorithm has identified this as an enhanced convection interval. Additionally, it also identifies the recovery phase as as part of that convection interval. And then we go back into a growth phase. So SOFI identifies any time that isn't a substorm as growth phase. The reasoning behind this is that the authors believe that any time where you're not in a substorm, you're actively adding energy into the system. So that's the reasoning behind that. Additionally, it's perfectly valid to use this in a study. It only scores marginally worse than Newland-Gerlov. So on the left here, we've isolated all the SML methods. And on the bottom here, it's the non-SML methods. And it only scores marginally worse than Newland-Gerlov. Before I go on to what I've done with SOFI, it's first important to explain the DP1 and DP2 current systems, since SML/SMU measures the deflection of the ground magnetic field due to the westward/eastward electrojet. So on the right here, we have a schematic of the current systems in the northern hemisphere polar ionosphere. At the bottom, we have the footpoints of the field-aligned currents of the substorm current wedge, so downward on the eastward and upward on the westward edge. And the DP1 substorm electrojet flowing across the ionosphere between these 2 points. As DP1 flows in the same direction as the westward electrojet, we expect it to have the same deflection on the ground. We expect DP1 to only be enhanced by when the substorm current wedge forms, however, and the cross-tail current is closed via this pathway. As such, we expect the contributing station when the substorm electrojet is enhanced to be near midnight with no associated SMU enhancement. Along the dawn and dusk sectors are the westward and eastward electrojets, DP2 currents. These occur due to convection of magnetic flux over the polar cap. When convection is enhanced, there will be a decrease in SML observed with the contributing station at approximately dawn and with a coinciding increase in SMU due to the eastward electrojet. Again, I want to reiterate, SOFI distinguishes between substorms and convection, leveraging the physics of this by filtering out times when the increase of SMU is correlated with the decrease of SML. So using that information, we resolved MLT distributions from events identified by SOFI. So on the right here is just an MLT distribution with midnight at 0 in the center. Specifically, we resolved MLT distributions of isolated substorm onsets. So that is a substorm that goes growth, expansion, recovery, growth, and events due to enhanced convection intervals. So these are just the flagged events. We find that consistent with previous studies, the isolated substorm distribution is centered around local midnight, or slightly pre-midnight actually. And that the convection distribution is also consistent with where the westward electrojet DP2 current happens along the dawn sector. However, the isolated distribution shows a really obvious bump in the dawn MLTs where the convection is maximal. And this got us thinking that this is a bit suspicious. So what we did was we decomposed this distribution. So the first step was to fit the convection distribution from before to the isolated distribution. We constrained that the fit cannot surpass the isolated distribution at any MLT. And then we resolved the residual distribution that is the isolated substorms minus the convection fit. And we argue that this is due to DP1 alone, since you've taken out the DP2 contribution. However, you can spot that the residual distribution is still non-zero at non-DP1 MLTs. So you can see it's non-zero at 5. And also there's a small bump here at 14 MLT. So we reallocated those onsets occurring at 5 to 18 MLT to the convection distribution. And this gives us this probability distribution on the right here. So just go through this plot, there's a lot going on. The This is now in probability space, unlike count space like before. So we have in green the convection distribution with consistent with where the DP2 currents flow. In gray dashed and dotted lines, we have our resolved residual DP1 perturbation distribution minus the events at non-DP1 MLTs. And we find that this distribution is consistent with the Frey et al. Distribution of auroral onsets, offset by 1 MLT. However, this worried me for a little while, but however, that kind of makes sense because the auroral enhancements are expected to be shifted westward from the DP1 enhancement, as it's co-located with the upward field aligned current corresponding to downward flowing electrons. And then we also see that these decomposed distributions are consistent with the DP1 and DP2 resolutions of the Supermag network by the Shore et al. 2018 paper. This is a fantastic paper. I really recommend you read it. It's where they evaluated the spatiotemporal patterns that contributed most to surface external and induced magnetic field across a solar cycle. We see that where the Shore et al. DP1 and DP2 current perturbations peak, they match up well with the location of the full width half maximum of our resolved MLT distributions. So the black lines peak 10 MLT and the full 10, and the black lines correspond to where the peak of this westward electrojet or substorm electrojet, occurs. And they correspond to the full width half maximum of our DP1 perturbation. And the green lines correspond to where the peak amplitude is of the DP2 resolution from Shore et al. And they correspond to the full width half maximum of our DP2 perturbation. As the resolved DP1 distribution needs to be manipulated from the combination of both the isolated and convection events, we can say that even though SOFI attempts to filter out convection events, it's still contaminated with substorms. And I'd argue to say that any SML method will be contaminated with substorms. So to answer our questions from earlier, two simple questions again. What is causing the disagreement between different lists? It might seem like an obvious answer, but other magnetospheric phenomena. In the case of the Royal Magnetic List, the prime candidate is enhanced convection. And can we filter out these errors? Yes, but only statistically. Again, I've gone through post evaluating those events. It's very difficult to do on an event by event basis, as we cannot say with certainty if an SML bay is due to convection or a substorm, as the convection distribution still occurs at the substorm MLTs. So in conclusion, substorm onset lists show weak associations with one another. They have less than 50% event coincidence. If you were to use one onset list, we would recommend, when only using onset times, the Chu et al. Onset list, although this only covers up to 2015. If you're interested in more recent event studies with more recent missions, I would recommend using the Newell and Gerlov list, since that covers up to the Supermag network's resolution, so up to 2022, I believe. However, when you require the full substorm phase time series, so when growth, expansion, recovery occurs, recommend using the Forsyth et al. SOFI onset list, phase list, sorry. However, all of these methods that rely on ground magnetometers will be contaminated with non-substorm intervals, which I've shown you can filter out statistically, but more information than just electrojets is required to filter out the non-substorm intervals on a case-by-case basis. So yeah, thank you very much for listening. I'm happy to take any questions.
You, Christian, do you have any questions here?
I have a question. Nice talk, Christian. I really liked that, like the study, especially the first part. I wonder, it kind of caught my mind that these, like the these are all like a stationary Poisson process, basically like when a substorm happens or not. Have you looked into any like information theory angle towards this, like mutual information or something between different substorm onset lists to see like the degree to which they might be causally connected? Meaning like maybe the different phenomena they use to measure the substorms are like possibly not physically connected at all, or to a lesser degree than you'd expect. So I guess maybe to clarify my question, uh, you found they show weak associations with one another. Have you thought of any way to figure out, to what degree those associations are weak because of physics rather than just, people labeling things differently?
Yeah, so that's a really difficult one to solve. It's something I've thought about myself. I think there's a couple problem where you're trying to match in situ data with continuous grand magnetometer arrays, right? Yeah, whether it's difficult to disentangle whether the physics is weak, like it's something different, because you don't have the resolution you need to have in the well, at geo or in the tail to be able to say whether there's less of a physical link than we thought. It's also with my method, it's not something I don't think you can answer yet because we've shown that there is weak associations. I think you need to go to finer timescales, but the struggle is that the error in the timing when you go to finer timescales becomes more of an issue.
Right. Do you think there could be, just as a follow-up question, do you think there could be some optimal time resolution to sort of match these together, with minimal error, or is that kind of unclear?
From my work, it's a bit unclear right now. Yeah. But maybe someone else has an answer.
Yeah, Christian, is there any merit? I don't look at substorms myself, so I don't know a whole ton about them and like how they get created besides what you just showed us. But is there any merit to like using an ensemble of lists instead of just like one of the lists to do substorm studies? If they're coming from different places, you figure you may be able to see different things when you combine them all.
Yeah, so that's a good question. There's a paper by John Heidechek that argues that there is merit in using an ensemble. Again, you run into problems where you can't rule out. It's a couple problem where you multiple signatures appearing doesn't mean it is exactly a substorm, and also just because you've missed out on one signature, it doesn't mean you can rule out that substorm. Does that make sense? Because your spacecraft might just be in the right position. You're over the Siberian Gap in Supermag. Yes, there is. If we had a perfectly distributed grand magnetometer array and a perfectly distributed geo, there's merit to doing that.
Yeah.
I think it's reasonable doing it in the meantime. You have a more robust list of substorm events.
That's exactly what it was supposed to ask. Okay. I would have another question. Please go ahead.
Hi, this is Lynn Kistler. So we've done some studies. I mean, to me, in terms of the physical processes that are a substorm, the dispersionless injections are kind of the closest to, the reconnection occurring in the tail leads to those injections. So I would certainly expect those to be a fairly good signature of the substorm. So the fact that nothing else agrees with it, to me, it just says that the other ones, that the magnetometer measurements aren't so good. But and I'm surprised by that you say that the injections don't have any correlation with the auroral images, because we did a study. Actually, we were the ones that first worked with Fry and got him to develop that substorm list. And so we had a bunch of substorms that we'd identified from the dispersionless injections, and then he developed his list from image, and we compared those. And we did have a lot where they agreed, and then we had a lot where image just had no data. And the number of events where one of them saw a signature but the other didn't those also existed, but were relatively small. So I'm a little surprised by the results that you show, that the dispersionless injections don't seem to correlate with other things. Do you have any comment on that?
Yeah, so firstly, I counted for the image orbit. Firstly, I took out times where image couldn't.
Right, I would hope so, yeah.
Yeah, I just wanted to clarify that. But I think
Yeah.
it possibly is due to the automated algorithm applied to the Llano SOPA. So I don't think it's as robust as the authors would like it to have been. I think it's one of those things where I think you have to still identify the dispersionless injection by eye, rather than trying to, if I believe correctly, they condensed the data to a singular scalar, relying on like entropy fit, I think. And I don't think it's robust in identifying substorms compared to just viewing it by eye. But then you're relying on the subjectivity of an author again. So
Right. Anyway, yeah, we also did a similar study because we're still trying to do a superposed epoch analysis of auroral outflow during a substorm, and so we looked at various substorm lists, and we also found the same thing, that none of them agreed. But actually, when we used different ones, they all did seem to show, more outflow after the onset and stuff. So it seemed like they were all giving kind of, it was at least believable that they were identifying substorms, but they just all weren't identifying the same ones. I don't know.
yeah, I think they are identifying substorms. It's just that they're also identifying, especially the grand magnetometer lists, they're also identifying lots of other things.
Right.
Yeah, I think the number of true substorms is actually a lot lower than what the list would make you believe. I think there's some work by Steve Milan. It was in 2021. He reanalyzed 2010. And in SOFI, we identified about 1,600 substorms in that year, and his reanalysis only evaluated. So he looked at as well as SML, SMU. He also looked at the polar cap flux, and he only saw 550 substorms in that year. So quite a big discrepancy
Right.
in number of events. Yeah. Thank you for your question, though. Thank you, Lynn.
Yeah. Oh, thanks. It was an interesting presentation.
You have a question? I forgot I had one. It was, but yeah, it was related with the lists. Like, since we have none of the lists agree with each other, doesn't mean that one listing there is a substorm or not, doesn't mean that it is a substorm property. No, because for me, like as Dr. Lin mentioned, like the list based on the injections should agree with the auroral observations, something like that, those identifications. And doesn't mean that the other lists, they are not substorm themselves, right? So there's a problem identifying the set itself here. I don't know. Anyway.
It's a couple problems because I don't think there's no ground truth, right? So we don't have a common, everyone's speaking their own language of what a substorm is. Yeah.
Okay.
Yeah.
Great presentation.
More difficult, more problems for everyone to solve.
Cool. All right, let's thank you, William.